So, hi everyone. Welcome to our third talk of NCU-Delta online talk series. So I think there might be some new audience here. Every time we have new audience. So bear with me. I have to do some, introductions. So for those you haven't heard it before, this talk series will be given by the awardees of NCU-Delta Young Astronomer Lectureship. So this award was established by the National Central University and the Delta Electronics Foundation to recognize young scholars under the age of 45 who have made outstanding contributions in this field. So each year, the awardee will be invited to Taiwan to interact with the local astronomers and the public. So I think the first award was given almost 10 years ago. So the original plan for this year was to invite all previous awardees to come to Taiwan, but we have decided to make this online due to this COVID-19. So our speaker today is Professor Nissim Kanekar from National Center for Radio Astrophysics of Tata Institute of Fundamental Research. So it's really our great pleasure to have him here. So I think Nissim received this award in 2015, and he's a world expert, especially in radio, and has received many fellowships and awards so far, such as Jansky Fellow, Max Planck Fellowship, and recently, I believe, he just got the Shantiswar Bandakar. Sorry, this is Indian, so yeah, forgive me if I didn't pronounce it correctly. So in 2017, yeah, I think this is one of the highest science awards in India, and I think he has made great contributions in many areas, including evolution studies of the evolutions of fundamental constant and evolution of formation of galaxies, interstellar medium using radio observations. So today, the title of his talk is Atomic Gas in Star-Forming Galaxies at High Redshift. So just a few announcements before we start. Please mute yourself during the talk. And if you have any questions or comments, you can leave them in the chat box anytime you want. And we will come back to those questions in the middle of the talk or during the Q&A after the talk. Okay, so great. So Nissim, I would let you take this away if you're ready.
Great, yeah. Thank you, Yenchen. And thank you very much for the invitation to speak. I'm sorry that I can't be there physically, but that's the way it is these days. I should say at the start that I tend to speak really fast, as you may have noticed. And I try to slow myself down in every talk, but I usually forget in about 5 minutes. So in case I forget, please, just say something in the chat box, and Yenchen will unmute himself and tell me to slow down. I'm going to be telling you about observations of atomic gas at high redshifts, high over here being redshifts of 1. And these are observations done with the telescope, the Giant Metrewave Radio Telescope, which is the array that you see in the background of this image. You can see a bunch of antennas over here. The picture is taken from a hill above the telescope. And the bulk of the work has been done by two outstanding students, Apurva Bera on the left over here and Aditya Chaudhary on the right. I will be focusing more on Aditya's work just out of interest of time and because that's a slightly higher redshift. And the other people involved in this work are listed over here. So let's move on. This is the broad outline of the talk. And then I'll get to the centerpiece of the talk, namely measuring the atomic gas mass of galaxies via H1 21 centimeter emission studies. I'll spend some time telling you, how we do this and the new technique that we are using, which is based on what is called 21 centimeter stacking of the emission signals of multiple galaxies. I'll tell you a little bit about the upgraded Giant Metrewave Radio Telescope, the UGMRT as it's called, and why it is so good for 21 centimeter stacking. And then I'll move on to the three main results I'll be talking about today. One is based on the 350-hour L-band observation of the extended Groth strip, the EGS. Second one is based on a 400-hour narrowband observation with the original GMRT of the DEEP2 fields at redshifts of 1. And the third is based on a 520-hour integration on the same DEEP2 fields, but this time covering a much larger bandwidth and hence a much larger redshift range. And the last two will be kind of merged together. Start with the pilot survey and then move on to, and we'll show you results from the entire set of data in one go. So that's the broad plan of the talk. But before we get there, let's talk about galaxies. So galaxies are basically made up of a bunch of things. They're made up of stars, which are usually in the disk of a galaxy. They're made up of atomic gas, which I will call H1 from now on, molecular gas, molecular hydrogen, mostly H2, and which are usually sitting roughly around the stars. The H2 and the stars are normally closely associated. The H1 is often more extended. And that's the interstellar medium of a galaxy. The interstellar medium, the ISM, contains metals and dust as well. And that's all part of the galaxy itself, so which is in the disk, in say the thick disk of the galaxy. But all around the galaxy, there's a circumgalactic medium. And this figure from Jason Tomlinson in an annual reviews article a few years ago gives you a nice summary of the physical processes going on. So this shows a disk of a galaxy, which is over 15 kiloparsecs in size and radius, which you can see by the small bar over here. And the disk is rotating. And you have this large region around it, which is about 500 kiloparsecs in size, half a megaparsec, and that contains lots of diffuse gas. And gas from this region, which is called the circumgalactic medium, is essentially accreting onto the galaxy. And this is mainly ionized hydrogen. And that's accreting onto the galaxy, and it's flowing into the outskirts of the galaxy. And as it flows onto the galaxy, the gas basically condenses into the disk of the galaxy, and it forms atomic hydrogen, H1. The H1 then cools and in local regions, and usually via metal radiation emission, and it forms molecular hydrogen, H2. And the H2 then fragments under self-gravity and forms stars. So that's the process of star formation in a galaxy. But what happens next? What happens next is that stars live their lives, and then at the end of their lives, the bigger stars go supernovae. And they throw a whole bunch of metals into the interstellar medium of the galaxy and also outside the galaxy. So they basically blow winds that go outside the galaxy. And so you wind up with the metals in the galaxy, and these cause further cooling of the atomic gas, which cause further formation of molecular hydrogen and further formation of stars, and hence further formation of supernovae. In addition, the outflows that are blown away from the galaxy, which are shown over here by these arrows going out away from the disk of the galaxy, these outflows drag back gas from the circumgalactic medium and pull it back onto the plane of the galaxy. And so you have recycling of gas that happens, which is shown by these curved arrows over here, and which also drags down some amount of gas from the circumgalactic medium onto the disk of the galaxy. And so outflows result in recycling of the gas, but they also can actually balance gas infall because there's some flow going outwards. And so gas which is falling into the circumgalactic medium can meet these outflows and stop the inflow, so to speak. So a galaxy is a very complicated beast, and it involves not just the actual physical parts of the galaxy, but also a large region, its sphere of influence, if you like, which is about a factor of 30 to 40 bigger than itself. So a galaxy is typically 10 to 30 kiloparsecs in size, and a circumgalactic medium might be 500 kiloparsecs or more in size. And so the issues now over here are, to form stars, you need to have gas accretion from the circumgalactic medium. You need to have cooling of the accreted gas to form atomic hydrogen. You need to have further cooling of the atomic gas, of the atomic hydrogen to form molecular hydrogen. And then you need to have fragmentation of the molecular hydrogen to form stars. Those are the processes that give rise to star formation in a galaxy. So now, if you want to understand galaxies, what do you want to understand? What you want to understand, first of all, of course, are the stars themselves. So you'd like to know what is the stellar mass of a galaxy? What is the star formation rate of a galaxy, the current star formation rate? What's the star formation history of a galaxy? Did it form stars in a quiescent way, just continuously at some star formation rate? Was it starbursty? Did it suddenly ignite in star formation and then become quiet again? What is its history in terms of star formation? And the way you do this, the way you probe the stars and galaxies are via ultraviolet observations, usually, which give you access to young and massive stars, via near-infrared observations, which give you access to older stars, optical observations, of course. Optical spectroscopy, for example, is extremely useful for this. Mid-infrared observations, which can give you information about the star formation rate. Far-infrared observations, which actually probe the dust, which is heated by the ultraviolet radiation from the stars, and then emits in the far infrared. So by observing the far infrared, you can actually get information about the star formation rate of a galaxy. And similarly, the radio, because in the radio, you can observe the supernova remnants, which are again produced by the death of massive stars, and also H2 regions produced by the ionizing radiation of these massive stars. So the stars can be observed, the stars or their effects can be observed over a wide range of frequencies or wavelengths, ranging from the UV all the way up to the radio. And we have lots of information about the stars. Molecular hydrogen, which is the step which is just next to the stars, we'd like to understand the mass of molecular hydrogen in galaxies. And we'd like to understand a kind of funny construct called the cosmic mass density. That's the density of molecular hydrogen at any epoch in the universe, integrating over all the galaxies in the universe. And that tells us about the buildup of molecular hydrogen in galaxies, not about just one galaxy, but about an average over a lot of galaxies. And the standard tracer of molecular hydrogen is CO rotational transitions in the millimeter and submillimeter. And these have become a huge tool over the last decade with the advent of ALMA. And so now we know much more about CO at high redshifts than we knew, say, in the 2000s. The next step in the process, going backwards, is atomic hydrogen. Again, we want to know the mass, and we want to know the cosmic mass density of atomic hydrogen in galaxies. And to get the mass, the only way of getting the mass that we know of today is via the H1 21 centimeter hyperfine line of atomic hydrogen. And that's at a frequency of 1420 megahertz, very low frequency. And so you need radio telescopes to observe this line. And you observe this line in emission. That's the only way of getting the atomic hydrogen mass of galaxies. The other way of probing atomic hydrogen is via Lyman alpha absorption. And this actually has been an interesting tool for the last 30 or so years, observing what are called the damped Lyman alpha systems towards background quasars. And R.T. Wolf and collaborators have used this technique, and many other people as well, but R.T. Wolf really led the field, to measure the cosmic mass density in atomic hydrogen and its evolution, all the way down from redshifts about 5.5 or so to the nearby universe, say redshifts of certainly 1.5 or so. And then you can use 21 centimeter emission studies in the nearby universe, redshifts of 0, to also get the cosmic mass density and compare the two. And you find that things change by about a factor of 2 from redshifts of roughly 3 to redshifts of 0 in terms of the cosmic mass density. But we don't know anything about the actual mass of galaxies in atomic hydrogen. Because to do this, you need to observe the 21 centimeter emission line. And that's very hard to do, as you will see in a short while. Finally, the circumgalactic medium, which is which is where all the gas comes from in the beginning. And you'd like to get the mass of this gas. You'd like to get the temperature of this gas. You'd like to get the metallicity of this gas. You'd like to see how much of effect the galaxy has in terms of throwing metals out. And the way you do this is via ultraviolet absorption, typically, by X-ray or UV emission. And you observe these highly ionized species, O6, O7, things like these, C4, in the circumgalactic medium. And you get a feeling for for where the metals are distributed around the galaxy. And an excellent review article is by Jason Tomlinson a few years ago. And so how do we quantify these processes? A good quantifier is what is called the depletion, is timescales basically. And so one way of quantifying it is the consumption timescale or the depletion timescale, which is the timescale on which the molecular hydrogen, for example, would be eaten up by the process of star formation. And so that's simply the H2 depletion timescale is simply defined by MH2, the mass in hydrogen, in molecular hydrogen, divided by the star formation rate. And that just says that, okay, if I keep forming stars at this star formation rate, how long will it take for all the molecular hydrogen to be eaten up? Simple metric. And that means that if I don't form more molecular hydrogen before the molecular hydrogen is eaten up, star formation will stop. So it's a good metric for how long star formation can last without adding more molecular hydrogen. Very similarly, you have the H1 depletion timescale. Again, the H1 mass divided by the star formation rate. And that tells you how long star formation can last without the addition of more atomic hydrogen from the circumgalactic medium. And then, of course, there is the gas accretion timescale. On what rate does the gas accrete onto galaxies from the circumgalactic medium? And this is an interesting issue by itself. This depends really on the nature of the accretion, on whether accretion happens by what is called the hot mode, where things basically come in more or less spherically, and then are heated to the virial temperature of the halo, which is about 1,000,000 degrees Kelvin, and then they have to cool. And this process is very slow. The alternative, and this is the classic picture of galaxy formation, which goes back to Rees and company in the 70s. The other way of having gas accretion is what is called the cold mode, in which gas flows in not spherically, but along filaments. And that's the kind of picture that you saw over here, where the accreting gas is coming in along, a long filament in the circumgalactic medium. And over here, in the cold mode, the gas is not heated up to the virial temperature of the halo. It actually accretes at about 10,000 degrees Kelvin or so. And the effect of this is that you don't have to spend much time cooling. So the process of accretion can be much faster. Now, the question is which of these modes dominates, and that's been a huge issue of debate over the last 15 or so years since Dushan Keris's fairly seminal paper in 2005. And the third way in which you can add gas onto galaxies, of course, is mergers. You just take two galaxies, bind them together. Minor mergers, you would add gas to the bigger galaxy and also fuel star formation. Major mergers, you will form a starburst almost certainly. So these are the three ways in which you can add gas to a galaxy. And the question of which of these dominates at which redshift and for which kinds of galaxies are important questions in galaxy formation and evolution.